students of 5 different age groups in the same class. Trying to teach different subjects and handle different levels of complexity for each student would result in a lot of confusion. Students in a school are allocated to classes based on the age group they belong to. It is because students in a class are likely to have similar attributes in terms of the level of knowledge, capabilities, height, and weight. Similarly, there are over 100 elements known to us. Scientists felt the need to classify them on the basis of some common properties. In this lesson, we will learn how the attempts to classify elements led to the evolution of the periodic classification of elements. At the end of this lesson, you will be able to examine early attempts at classification, analyze Daubernier's law of triads and Newland's law of octaves, compare the merits and demerits of the law of triads and the law of octaves, list the main features of Mendeleev's periodic table, and analyze the merits and demerits of Mendeleev's periodic table. The earliest classification categorized elements into metals and non-metals. However, this classification served only limited purpose because of the following reasons. The classification was at a very broad level. A large number of elements were classified as metals. However, they did not necessarily display similar chemical properties. For example, sodium and copper were both characterized as metals, but their chemical properties are very different. Some elements, such as boron, exhibited the properties of both metals as well as non-metals. It was difficult to determine how to classify such elements. After further research, a German scientist, Daubernier, arrived at a hypothesis in the year 1829. According to Daubernier, all elements occurred in groups of 3 when arranged in increasing order of atomic masses. He referred to these groups as triads. Daubernier's law of triads states that the atomic mass of the middle element of a triad is the arithmetic mean of the atomic masses of the other 2 elements. To illustrate this law, consider the triad of lithium, sodium, and potassium. The atomic mass of lithium is 7, the atomic mass of sodium is 23, and the atomic mass of potassium is 39. The arithmetic mean of the atomic masses of lithium and potassium is 23. This is equal to the atomic mass of sodium. Similarly, in the triad of chlorine, bromine, and iodine, the arithmetic mean of the atomic masses of chlorine and iodine is approximately equal to the atomic mass of bromine. While this law worked for some elements, it was not a success because all the known elements could not be arranged in the form of triads. The law did not hold good for elements with very low or very high atomic mass. For example, the arithmetic mean of the atomic masses of fluorine, 19, and bromine, 80, which comes to 49.5, varies significantly from the atomic mass of chlorine, which is 35.5. Since Daubernier's law could not successfully group elements, the attempts at classification continued. The next attempt came in 1864 when an English chemist, John Newlands, stated his observations in the form of Newland's law of octaves. Newlands noted that when elements are arranged in increasing order of their atomic weights, the property of every 8th element is similar to that of the first element, similar to the first and the 8th notes in the musical scale. Consider the list of elements with their atomic weights in increasing order. Starting with lithium, the 8th element from lithium is sodium. Similarly, the 8th element from sodium is potassium. Lithium, sodium, and potassium show similar properties. For example, they are metallic in nature, have high reactivity, and conduct heat and electricity. Similarly, beryllium, magnesium, and calcium show similar properties. For instance, all the three elements are shiny and fairly soft. However, Newland's law of octaves failed because it was not valid for elements of atomic masses higher than calcium. Newly discovered elements could not find a place in Newland's table. Mendeleev based his work on the research by Newlands and took it further. He felt that effective grouping of elements and prediction of properties could be based on two parameters: atomic weight and chemical reactivity. Mendeleev's periodic law states that the physical and chemical properties of all elements are a periodic function of their atomic masses. Let's look at the features of Mendeleev's periodic table. The table had 8 vertical columns called groups and 12 horizontal rows called periods. In every group, a gradation of physical and chemical properties of elements was observed. The table provided gaps for undiscovered elements. The table helped predict the properties of 3 elements. These elements were named Eka, boron, Eka, aluminium, and Eka, silicon. When these elements were discovered, they were named scandium, gallium, and germanium. The properties of these elements were very close to those predicted by Mendeleev. Like other attempts at classification of elements, Mendeleev's periodic table also had some merits and demerits. Let's take a look at the merits first. The table helped in the correction of atomic mass for many elements. It predicted the existence of some elements that had not been discovered at the time that the table was created. Because of its merits, the periodic table is widely accepted as a system of classification. However, it did not achieve complete success because of some demerits. The table had some inaccuracies. For example, the table reversed the atomic weights of 2 pairs of elements. A. Iodine, with atomic weight 127, came after tellurium, with atomic weight 128. B. Nickel, with atomic weight is 58.68, came after cobalt, whose atomic weight is 58.94. Alkali metals such as sodium and potassium, and coinage metals such as copper, silver, and gold were placed in the same group, even though their properties are significantly different. Lanthanides and actinides were not given proper place in the periodic table. Isotopes did not find a place in the periodic table. The table did not clearly indicate the position of hydrogen. H. J. Moseley, an English physicist, built further on the periodic table to resolve the problems encountered in using it. He discovered that atomic number is a better basis for classifying elements than atomic weight. On the basis of his work, he developed the modern periodic law. The modern periodic law states the physical and chemical properties of all elements are periodic functions of their atomic numbers. The modern periodic law has become the universally accepted form of classification of elements, as it does not suffer from the demerits of Mendeleev's periodic table. Was intended to illustrate the arrangement of elements using atomic weight as the basis of classification. However, this arrangement showed some anomalies, like elements with higher atomic weights were placed before elements with lower atomic weights. For example, the atomic weight of cobalt is 58.94, and that of nickel is 58.68. However, the Mendeleev's periodic table places cobalt before nickel. Such anomalies were resolved when the modern periodic law designated atomic number as the criterion for classification. In this lesson, you will learn in detail about the modern periodic law and the modern periodic table. At the end of this lesson, you will be able to explain how the modern periodic table is arranged, explain the reasons for classifying elements on the basis of atomic number, describe the features of the modern periodic table, and identify the trends observed in the modern periodic table. The modern periodic law was developed by Moseley, an English physicist. This law states that the atomic number is a better basis for classification of elements than atomic weight. This law formed the basis for the modern periodic table. Atomic number is the number of protons in an atom. It is also equal to the number of electrons in the atom, since an atom is electrically neutral. For example, the sodium atom contains 11 protons and 11 electrons. Therefore, the atomic number of sodium is 11. Similarly, the atomic number of magnesium is 12. Since the atomic number of magnesium is higher than that of sodium, magnesium is placed after sodium in the modern periodic table. Electronic configuration of an atom is the arrangement of electrons around its nucleus, which affects the properties of the atom. Bohr, a Danish physicist, tried to explain the behavior of atoms through his atomic structure theory. According to his theory, electrons are not located randomly around an atom's nucleus, but occur in definite electron shells. Electrons in the outermost shell of an atom are the ones involved in chemical reactions. These electrons are called valence electrons. The shells in an atom can be named alphabetically as shell K, L, M, N, and so on. Each shell in an atom has a limited capacity for electrons. The K shell can accommodate 2 electrons. The L shell can accommodate 8 electrons. The M shell can accommodate 18 electrons. The N shell can accommodate 32 electrons. As the lower shells are filled up, the additional electrons are placed in more distant shells. Normally, elements show the following properties based on their electronic configuration. An element with 8 electrons in the outer shell is stable and does not normally enter into chemical reactions. For example, argon is an inert gas and does not react with other elements. However, if the outer shell has less than 4 electrons, the elements are reactive and give up electrons in chemical reactions. For example, sodium has 1 electron in the valence shell. It gives 1 electron to chlorine to form sodium chloride. If the outer shell has more than 4 electrons, the elements normally accept electrons in chemical reactions. For example, chlorine has 7 valence electrons. It accepts 1 electron from sodium to form sodium chloride or common salt. Let's examine the features of the table. Elements are arranged in the increasing order of atomic numbers. Horizontal rows in the periodic table are called periods, and vertical columns in the table are called groups. Elements in the modern periodic table are arranged in 7 periods and 18 groups. You can locate an element in the periodic table by referring to the relevant period and group. For example, sodium belongs to the first group and the third period. You can observe trends in the properties of elements as you analyze them across periods and down groups. Let's look at the basic trends in belief. The properties of elements change gradually from left to right in a period. As an electron is added to the outermost shell. For example, sodium is highly reactive and magnesium is less reactive as compared to sodium. There is a drastic shift in properties between the last element of a period and the first element in the next period. For example, neon is inert, whereas sodium is highly reactive. Elements in a group display similar properties because they have the same number of electrons in the outer shell. For example, sodium in period 3 and potassium in period 4 belong to group 1. Both these elements are highly reactive and metallic in nature. Elements are placed in periods based on the number of shells in their atoms. That is, the number of shells in the atoms of all elements in a period is the same. While moving from left to right in a period, the atomic number increases by 1 unit at each step. This means that a valence shell electron is added to the atom. Consider the example of the elements in period 3, which have 3 shells, K, L, and M. The third shell starts getting filled as we move from left to right in the period. Thus, the first element in this period, sodium, has 1 electron in its valence shell, while the last element, argon, has 8 electrons in its valence shell. Let's take a look at the basic characteristics of each period in the table. The first period is the shortest period and contains only 2 elements, hydrogen and helium. The second period contains 8 elements, from lithium to neon. The third period also contains 8 elements, from sodium to argon. The fourth period is a long period and contains 18 elements, ranging from potassium to krypton. The fifth period contains 18 elements, starting from rubidium and ending at xenon. The sixth period contains 32 elements, from cesium to radon, which also includes 14 lanthanides from cerium to lutetium. The seventh period is incomplete at present and can accommodate 32 elements, which includes 14 actinides from thorium to lawrencium. It will be filled up as new elements get discovered, as is expected. In addition to the 7 periods across, the periodic table is classified into 18 groups vertically. The classification in groups is based on the number of valence electrons in an atom. The number of valence electrons of elements down a group is the same. Therefore, the elements in a group show similar physical and chemical properties. Let's take a quick look at the properties of the elements in each group to examine their similarities. If you begin with group 1, this group has 7 elements: hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Elements in this group contain one valence electron. That is, their general outer electronic configuration is ns1. Because of their configuration, they enter into chemical reactions easily. That is, they are highly reactive. All these elements form basic oxides that react with water to form alkalis. So the elements of group 1 are also known as alkali metals. For example, sodium reacts with oxygen to form sodium oxide, which then dissolves in water to form sodium hydroxide. Let's now look at the elements in group 2. The elements of the second group are beryllium, magnesium, calcium, strontium, barium, and radium. These contain 2 electrons in the valence shell. That is, their general outer electronic configuration is ns2. These elements are also known as alkaline earth metals, since they hydrolyze easily to form alkaline solutions. For example, magnesium oxidizes to form magnesium oxide. This compound can be dissolved in water to form magnesium hydroxide. The next group is group 3. The elements in this group are boron, aluminium, gallium, indium, and thallium. Group 3 elements have 3 valence electrons. Hence, their general outer electronic configuration of atoms here is ns2np1. These elements form covalent compounds that are formed by mutual sharing of electrons. For example, boron trichloride is formed by the sharing of 3 electrons between boron and chlorine. Let's move to group 4. The elements in this group are carbon, silicon, germanium, tin, and lead. These elements contain 4 valence electrons, and their general outer electronic configuration is ns2np2. The elements in this group combine with halogens to form the respective halides. For example, carbon combines with chlorine to form carbon tetrachloride. In the same way, silicon combines with chlorine to form silicon tetrachloride. Next is group 5. The elements in group 5 of the periodic table are nitrogen, phosphorus, arsenic, antimony, and bismuth. These elements contain 5 valence electrons, and hence their general outer electronic configuration is ns2np3. These elements react with hydrogen to form hydrides. For example, nitrogen combines with hydrogen to form ammonia gas. Similarly, arsenic combines with hydrogen to form arsine. Let's now consider group 6. The elements of group 6 are oxygen, sulfur, selenium, tellurium, and polonium. These elements contain 6 valence electrons, and hence their general outer electronic configuration is ns2np4. These elements react with hydrogen to form hydrides. For example, water and hydrogen sulfide. Group 7, the group of halogens, is next. The elements of group 7 are fluorine, chlorine, bromine, iodine, and astatine. They contain 7 valence electrons, and hence their general outer electronic configuration is ns2np5. The elements in this group are also known as halogens because they have originated from the sea. These elements have the tendency to gain electrons and become stable. This property helps in the formation of compounds with alkali metals. For example, chlorine accepts one electron from sodium to form sodium chloride. The last group is group 8, or the zero group. The elements in this group are helium, neon, argon, krypton, xenon, and radon. All these gases, except helium, have highly stable Ns2-Np6 electronic configuration in their outer shell. Helium has 1s2 configuration. They are also known as inert gases because they don't react with other elements. You can see that in every column that represents a class, the height of the students increase from the front to the back. You also see a decrease in height from left to right in each row, which consists of students from different classes. A similar gradation is seen in the properties of elements in the periodic table. You can observe regular changes in the properties across periods as well as down groups. In this lesson, you will learn about periodic properties and the trends of periodic properties across a period and down a group. At the end of this lesson, you will be able to define the term periodic properties, explain the significance of periodic properties, and describe the trends of periodic properties across a period and down a group. The term periodic properties in elements refers to the properties that recur at regular intervals. The trend of recurrence of properties is called periodicity. The important periodic properties of elements are atomic radius, ionization energy, electron affinity, electronegativity, and metallic and non-metallic character. We will look at each of these properties in detail to find out how they vary across a period and down a group. Atomic radius is the distance between the center of the nucleus and the electron present in the outermost energy level or orbit of an atom. Atomic radius is expressed in angstrom units. 1 angstrom equals 10 to the power minus 10 meters. Let us now analyze the variation in atomic radius. Atomic radius decreases across a period. This happens due to the addition of a proton to the nucleus, which increases the positive charge. This pulls the valence electron inwards, resulting in a decrease in the atomic radius. Fluorine, a halogen atom, has the smallest atomic radius of 0.72 angstrom units. On the other hand, atomic radius increases down a group. This is because when you go down a group, electrons enter a new principal energy level, and the number of shells in the atoms increase. Therefore, the size of an atom increases down the group. In the periodic table, cesium, Cs, an alkali metal, has the highest atomic radius of 2.62 angstrom units. The second periodic property is ionization energy. Ionization energy is the minimum energy required for removing the outermost electron from a gaseous neutral atom to form a cation. The unit for ionization energy is electron volts, or kilojoules per mole. An example of ionization energy can be observed in reactions involving sodium, where 496 kilojoules of ionization energy is needed for the formation of a cation. Let's now review the variation in ionization energy. Ionization energy increases as we move across a period from left to right. This is because the decrease in atomic size results in an increase in the nuclear attraction, thereby increasing the ionization energy. This is why inert gases possess the highest ionization energy. Helium has the highest ionization energy in the periodic table. Down a group, the ionization energy decreases due to an increase in atomic size. In the periodic table, alkali metals possess low ionization energies. Cesium, an alkali metal, has the lowest ionization energy. Next, let's look at the third important periodic property, electron affinity. Electron affinity is defined as the energy released when an electron is added to a neutral gaseous atom. The unit for electron affinity is kilojoules per mole. Consider a fluorine atom. In the gaseous phase, a fluorine atom releases 328 kilojoules per mole when it gains an electron to form a fluoride ion. Let us now observe the variation of electron affinity across a period. Electron affinity increases from left to right in a period. This occurs because across a period, the tendency to gain electrons increase with a decrease in atomic size. Halogens in the periodic table have the highest electron affinity values. Electron affinity decreases down a group. This is due to the tendency to gain electron decrease with an increase in atomic size. The zero group's elements or the inert gases have the lowest electron affinity values in the periodic table. Generally, electron affinity values are negative because electron affinity involves the release of energy. Let us now talk about electronegativity, the fourth important periodic property. Electron negativity is defined as the tendency of a bonded atom to attract the shared electron pair towards itself in a molecule. Note that this property is observed only in the atoms in a molecule. Let's review the variation in electronegativity in the periodic table. Across a period, electronegativity increases from left to right. As smaller atoms are more electronegative than bigger atoms. In smaller atoms, the outer shell is very close to the nucleus and hence the attraction between the nucleus and the electrons are stronger. In the periodic table, halogens have high values. Fluorine possesses the highest electronegativity value of 4.0 in the periodic table. Down a group, the tendency to attract the electron pair, or electronegativity, decreases as atomic size increases. In the periodic table, alkali metals possess very low electronegativity values. Cesium has the lowest electronegative value of 0.7. The last important periodic property is metallic and non-metallic character. Metallic character is defined as the tendency of an atom to lose electrons. The tendency to lose electrons is due to low electronegativity or high electropositivity. Non-metallic character is the tendency of an atom to gain electrons. Now, observe the variation in the metallic and non-metallic nature of elements in a group and in a period. Across a period, metallic character decreases and non-metallic character increases due to an increase in electronegativity. So, the tendency to lose electrons or metallic character increases. For example, cesium has the most metallic character and fluorine has the most non-metallic character. Down the group, the metallic character increases or the non-metallic character decreases. This is because the increase in the atomic size decreases the electronegativity, which increases the metallic nature or decreases the non-metallic nature. From the trend, you can make out where the metals and non-metals should be positioned in the periodic table. Metals are placed on the left of the periodic table non-metals are placed on the right side, and metalloids are placed between the metals and the non-metals.